one of the terms that's often used. So elasticity or plasticity are terms that are often used in neuroscience to describe the capacity of a model to adapt. Mental plasticity is the ability of the model to sort of reconfigure. It's the ability of the brain to learn new tasks, right? So as you get older, some of the flexibility of your brain's modeling structure reduces as a result of sort of integrated bias integration, long-term bias integration. So it becomes a lot harder to potentiate anything new with respect to the large corpus of information that you have. If you think about it this way, the longer you get in life, the more information you've built out, the more prior you have, the higher your pi density estimate is, right? So the more information you have. Thus it takes a lot more information to override that. It takes substantial amounts of evidence, a preponderance of it, in order to subvert your natural expectation. Models are the same way. So when you train a model with lots and lots of data, we remember what we saw with BCI and the R-squared criteria. We noted that they took into consideration pretty strongly the amount of data that you had to support whether or not you could use more features. So the idea here is that the lasso is actually a more aggressive form of ridge regression, of the L2 regularization. Why is the L2 regularization a little bit softer? Well, it only really starts to have a softer characteristic on the lower end of the spectrum. It's actually weird in two ways. The penalty for the square is higher, technically, if what? The value is much greater than 1. So that the absolute value for a system of coefficients that are around 1, L1 and L2 work effectively the same. As the value gets below 1, as you get into small fractions of determinacy, what happens with L2 regularization? Actually, so the square will start off by moving more slowly towards it below 1, right? But that's the weird thing about the square. The square is that past 1 it blows up, below 1 it goes down, but it goes down much more slowly with the square and goes up more quickly with the square. What happens with the L1 regularization? It's linear in both directions. It goes at the same speed on both sides. So that's the interesting part of it. That the high linearity characteristic of just using the quantity of the total coefficient makes it to where the system will penalize either large coefficients or small coefficients in roughly the same way. But here's the other consideration. If you look at the bulk, this is RSS, right? This is just residual square. Look at the bulk of the amount of the coefficient times the lambda. What happens with data that has very high variance? It's not actually going to be affected much, because if there's still a pretty high RSS, that's a quantitative number. So it will take quite a bit of lambda pressure. The lambda has to, like, when I say that's the scale penalty, that's like the ratio of score loss. So you guys have seen, some of you guys even may have had the experience. Have you guys had the experience of losing points when you answer a question incorrectly? Yeah. Right. It's not common in Western education system for us to do what we call a guess penalty. But guess penalties can be used. Effectively, this is a type of guess penalty, where I say, if you must err on the side of anything, err on the side of caution, and just say there is no correlation, right? So this is an implication to the strength of correlation. I'm trying to actually get you to err on the side of caution and not answer the question if you're unsure about it. So that's one of the mechanisms that we could look at with regard to the L1 regularization. So what happens whenever the absolute value of a coefficient goes towards negative, or not toward negative, but toward 0, right? So towards 0, it converges toward that absolute direction, right? There can be negative or positive values. You can either have a negative correlation or a positive correlation. Either slope works. It's the reason why we have to have an absolute or a square to deal with it. But as it's further away from the center the values effectively converge. Now that's what I was going to show you with respect to this graphic back here. If we look at the scale of the coefficients initially, this graphic is hard to understand until you sort of take it in the direction of looking at respective scale of lambda with respect of just the absolute value of the coefficients, because this is a weird part. This slide's in front of L1 regularization. It's not for L2 because those aren't squares. Okay, so let's look here, what's going on. Large coefficients with incredibly small values of lambda, right? This is 10 to the negative 2. So what's 10 to the negative 2? Like 0.001 for a scaling coefficient. This means that even if you had an error factor of 1, that would be a coefficient of 1, you'd still only add 0.001 to the RSS. Let's imagine that you had a scaling factor of 10, a coefficient of 10. You're not only adding 1 to the RSS. What's the deal with that? Adding 1 to the RSS isn't a lot. It's not a lot. So while we think about this, we say that the tendency or the pressure is towards 0. Are all these technically going to flatten out? No, they're not. Because unless lambda is really big, right? This is lambda of 1,000. So what effectively happens here? Everything starts to get crushed. It's so penalized that the ratio of RSS to the ratio of any degree of coefficient, right, 0.001, is going to be almost the same as the residual penalty for the summation of the points on the data graph. RSSs, remember from your scoring and seeing what those values actually are and mean. A lot of times if you had an RSS, let's say you have 1,000 samples and your variance on those 1,000 samples is 0.02, you're still going to be what? An RSS of approximately 20. So when you're thinking about RSS with regard to the scale of the coefficients, at a scale of coefficient of 10 or 15, for absolute value for a low dimensionality system is not going to be a strong tip to that 20 or 30. Imagine when you have 10,000 samples, when you have 100,000 samples, all right? You have to get lambdas that are going to get a lot more aggressive in order to adjust for it. The whole scope here is just to pull it slightly off, attempting to overfit on a few dimensions with regard to coefficient restrictions. So as we start off with high coefficients, this is an implication that effectively for income rating it has a negative correlation of around like 290, right? And a positive correlation for limit of like 425. We're going to do 425 for the base standardization of coefficient for rescaling factor of likelihood for default rate. So it's saying for every $400 that you borrow, it has that relative correlation to your likelihood of increasing in your chances, right? So it starts off first, the first standard deviation away from a default rate, and then second, third standard deviations. So it would be like 3 standard deviations out would be 400, then 800, then 1200, right? Now you're into the center deviation of the system. Now you're starting to get closer to the offset. What happens whenever you get that past 1200, right? Now you're actually flipped over. Another 400, you're $1,600, you're into the default camp. So it's saying that effectively every standard deviation happens at approximately 400. This is just a rough estimate of what the coefficient actually represents, right? So for the residual grouping, we say big numbers of the value, relatively large coefficients for the standardization become less impacted by relatively small lambda, forcing us to select successively larger and larger lambda to start to effectively penalize the system. Now you can have any lambda, you can have any value of lambda. So let's look here real quick what we're discussing. As we said, the lasso does an absolute value penalty in a slightly different way. It just takes the literal absolute, it just drops the sign from the integer, right? So if either integer or decimal value, either one. So we said ridge regression will never totally converge to 0, because as the values of the coefficients get smaller and smaller, the square will, even if lambda is very large, it will never 100% converge to 0, because it would take a very long time. Now, effectively, can it converge to 0? Absolutely. Theoretically, L2 regularization can't converge to 0, but effectively, in actual process, L2 regularization could get so close to 0 that it was the same. It wouldn't reduce any computational complexity, but lasso will converge quickly or more quickly at large lambda, such that we end up with a situation where the relative amount of coefficient quantity becomes so small by continuing to reduce the absolute value, mostly by what? Increasing lambda. You get an increasing penalty scaling. I'm charging you more points for giving me anything that has even slightly positive coefficient. So more and more I charge you for giving positive coefficients, everything's going to eventually get slammed. And I'm going to do what? I'm going to say effectively overemphasize any correlations, to the point to where there will be certain correlations that do what? Their presence, literally having a coefficient relative to the correlation of the offset between the target and the input predictor value. You're adding enough variance with inclusion of that particular feature characteristic that it doesn't make it worth it. So the system will say, let's just go ahead and cut out all of that feature, and by zeroing that feature, I will eliminate all the variance and hopefully attempt to sort of converge down to a model that contains the fewest necessary elements. So minimization of this system can propagate into the individual coefficients such that it will try to min the total system, target and effective lambda. This particular graphic is a little odd, so it's hard to make a lot of sense of, but we could take into consideration a strict offset system. We have the attempt to push the system off the axis to try to drive the coefficients down. I have another picture I'll show you. I know, I don't really know what it means. To be honest, I've looked at this a lot. I see it, but it's so complicated to try to explain to you what the whole point of this is, that it's a bit, there's like a topographical characteristic to this. There's sort of a depth characteristic where the tightness of the lines implies the relative tightness of the coefficient. So if you had a two-dimensional system and you're attempting to optimize the coefficient characteristics, then utilizing this offset, where we look at the intercept characteristic of this sort of circular version of the graph versus the intercept coefficient characteristic with this square version, this linearized version, we note that it re-correlates the relationship of those two coefficients in such a way as to improve their correlative characteristics. It's just a model improvement process. And as I said beforehand, the ultimate goal is to try to get all features to be handled with roughly the same level of importance, right? Everybody should be treated equivalently or equally, or looked at as if it has a contribution. Actually, the idea would also, if we look back at that previous graph, would be disincentivizing the system from learning only from income and limit, right? So if limit and income are involved there, we say, well, why do you need other things? Like the inclusion of any other coefficient in this system is, I don't need any other features. Previously, we'd done what? We'd gotten rid of everything except for those last two features. Well, we know that maybe if we try to drive those coefficients down a little bit, we're thinking about it effectively overfitting to features in some senses. So this is another weird aspect to it. This is one of those things that's like, there's no good visualization for it. You just have to try to get your head around it. That by providing too few features, we tend to sort of put too much weight on too little of the actual evidence. You can think about that as being a type of overfitting because of the fact that if we have a little bit of information that is sort of spread out among several other features, we should take that information in consideration. You know, when we try to make decisions as humans, what do we try to do? We try to get all the facts, right? We try to get all the information so we make sure that there isn't something we missed, sort of the devil in the details. These models don't have that mechanism built into them. They don't incentivize that. They incentivize learning how to maximize the predictive capacity, minimum error with respect to fewest possible features, right? We've really kind of sit on their head until they get to the absolute minimum. These mechanisms of regularization try to say, let's be a little bit less like specific, sticking to only this one limited subset of features. There's another relationship to what happens here that will kind of correlate to something that we will do in the future, and we'll come back to it. But that is the idea that by reducing the relative flexibility of each of the linearities, you can reduce the effective degree of freedom of the model in a small way, right? So by penalizing the model for making any coefficient strongly positive, a high strong positive correlation, then we are going to disincentivize the model from only learning most of its information from a very few subset of predictors. This slide compares lasso and ridge. It's a little interesting, right? So as we change lambda, we also change the characteristics of the curve distribution. All right, so the left plot is a plot of the square bias in black, variance green, and the MSE, which is going to be that purple value, right? So for the lasso on the data. So what we're actually looking for here is a lasso characteristic, and then over here the ridge regression characteristic, right? So the R squared for so this one. So I thought the other one was R ridge regression. So this is lasso.
I think it's showing the square and the variance between the two.
Oh, I see what you're saying. Yeah, you're right. I was for some reason I was thinking the one on the right was a square, but it's an R square for characterization. Notice that as lambda goes to a effective, let's just look at the main characteristic here. What's the main characteristic? Lambda on the left-hand side, what happens as lambda increases? We notice that performance dip in the MSE with respect to the combined system. It has an absolute global minimum with respect to the graphic. That global minimum with respect to the graphic indicates what? That the lambda for the system is somewhere in the neighborhood of like 2, maybe 3, okay? How did we do that? We did a k-fold and averaged the fold performance as we increased lambda. So we start off with a lambda of 1, go to a lambda of 1.5, lambda of 1 or 2, lambda of 2.5, right? So step through, let's say, at half values of lambda. You could go down to smaller values. But the goal would actually be that you'd start off with a fairly big steps of the system, right? Get an idea of what's going on in the general trend and say, hey, as I increase lambda, what happens? It starts off pretty good, it starts off improving. Then maybe I get up to a point where I start experiencing a bit of a diminishing return of an increase in lambda. So then I would reduce the scaling and then maybe step back through until I got to an optimized point, right? You could take something like the gradient here. You take the the relative change in direction based upon the change in lambda of the MSE for that particular calculation, and end up with what? You end up with the positive direction, the direction of greatest increase. So you take the negative gradient of that surface, you end up with the direction of decreasing error. So we use something like what's called simulated annealing or gradient descent maximization. We're going to end up with the maximized functionality, maximized accuracy for the system, or minimized MSE, as a result of taking the gradient of the system as lambda changes. So as lambda value increases, we find that over there on the right-hand side of the x, what happens? We have a rapid swing back up towards a positive value. That's what we would expect, because what happens? We over-penalize it to the point where it really can't learn anything anymore. It doesn't assume any correlation between any relevant feature because all the coefficients have been so penalized towards zero that for the system to try to find anything of merit in the remainder amount of error that it can establish for, it doesn't really have any room. It doesn't have enough flexibility to fit the system. So effectively, it actually goes from an underfit situation, or maybe an overfit situation, to an underfit situation. This is the weird part of lambda, that the error at the end of the system is effectively underfitting. Previously, the error was effectively overfitting, right? Because what did we experience? Well, we experienced the overfit as a result of the characteristic of the training data becoming the only indicator of positive value output. But we notice here we have squared bias and system variance, variance being the intercorrelate capacity, and squared bias being the predictive capacity output. So predictive capacity output spikes and then plateaus. Notice, as lambda gets to a certain point, right here, maybe around something like 20 or 30, I think this has a really weird scale to it. I think it's a log. Like it looks like a log scale plot because it goes from 0.02 all the way up to 50. Often we'll show something like lambda on a log scale because it has a bit of a logarithmic relationship of its penalty complexity, because as I said beforehand, from either perspective, either value out from zero in each direction with either the absolute value or the square will gradually increase the grade of the penalty for the coefficient. The key factor to keep in consideration here is that over-penalize the model and it stops learning. It will eventually effectively become either it starts to overfit and then it completely loses everything, loses track of all of it once it gets to a certain value. Like I said, this plateau for the learning function effectively is a type of underfitting because all the coefficients have gone to almost nothing with respect to their calculated capacity. But we also notice what's the relative variance in the system. What happens here? What do we normally see? We saw that variance increased and bias decreased, right, typically. What's going on in this graphic? Bias is increasing in MSE and variance is going down. This literally is the opposite direction of the underfit overfit graph, okay? This is the opposite direction. This isn't overfitting, okay? Because you have, with so little flexibility of the system, you have high variance and relatively low bias, right? What happens as you increase lambda? Well, you get some of your variance back, variance reduces, and you get some relative functional decrease in accuracy. The overfitting has been mitigated, right? Think about this as effectively being sort of tacked on to the right-hand side of an overfit graph, right? So the overfit graph does what? The bias error, right, comes down and hits the bottom, right? So you say the relative error of the system bottoms out. The variance has maximized. So you start off in this case over here, we go, oh wait, the variance is high initially, set to set interdependence, high initially. What we would normally see as we increase the flexibility, we'd see low variance initially for low dimensionality, right? Set to set, it would be relatively low variance because the training and testing should have approximately the same level of performance for a low flexibility model. But this graphic is starting off with what? High flexibility model. So it's saying, look, with this high flexibility model, we've got a lot of variance, but we've got good accuracy, right? The model's good. We've got all of our features are there. All of our features are allowing us to fit. We instantly overfit, okay? So overfit happens here. Like I said, what happens on this side? This is underfit. Why underfit? Because effectively it's driving the reaction into reverse. It's now penalizing even for the inclusion of that particular feature. Whenever we think about this, we typically tend to think about it with respect to flexibility, right? This is a flexibility penalty. The greater the penalty of flexibility that I assume, the closer it becomes to some effective degree of freedom, right? It is effectively a lower degree of, or a lower dimensionality. This is the other portion of it. Okay. The effective degree of freedom with respect to dimensionality for the ridge regression. The dimensionality stays the same, right? But what happens as lambda goes up?
Dimension reduces?
The dimensions don't reduce, it's the same dimensionality. But the effective flexibility reduces, right?
Yeah.
The capacity of the model to fit onto that data.
Reduces.
We start off with a highly flexible model, right? That allows us to make changes based upon individual regions, right? We can adapt the system to fit in this space. But if I take something that's more rigid, right, that has more solidity, less flexibility, right, it doesn't allow us to push this. Actually, it's more flexible. What are you talking about? Maybe something, right, a thicker piece, less flexibility to be able to push through it, all right? So what we're doing in truth, what we're doing to this system, we're increasing the thickness of it, kind of, right? We're increasing the thickness of it. We're making it more rigid, harder for it to effectively overfit. We're penalizing any possibility of changing directions on all of these different systems. The coefficient pushes towards zero. What happens as the coefficient pushes towards zero? There's less relative contribution of that particular feature to the overall consensus of our understanding of the system. So the less relevant contribution is an effective degree in reduction of dimensionality. Here's the ridge regression version. I forgot. Yeah, this one's ridge. Notice there what happens as well. Variance bottoms out. Yeah.
On the last graph, is the intersection of bias and variance not what you're shooting for? Isn't that kind of like equilibrium?
Yeah, notice what happens though. Notice what happens at MSE.
It jumps
right?
a lot quicker.
So MSE, purple MSE right here.
Mm-hmm.
We said previously this would be kind of the idealized set point, right? It's the perfect intersection between the system. But notice the MSE is what? It's going to be based upon testing and training. So it is the average MSE.
Okay.
So
And that's not
average
taking in
MSE
the
includes both the training set, which actually from a numerical standpoint outweighs it. But we noticed something. We said, well, we could theoretically attempt to maximize what? Maximize bias, maximize our bias, our accuracy. Right? So just substitute the relative term bias for training accuracy.
Okay.
From here forward, that's honestly the best way to do it. I've done this in the past. I think it works well enough. Let's just reprogram our brains for when we see this term bias in the training output. Rewrite that in your brain to read training accuracy. Because that's what it is. That's what it is, okay? So training accuracy goes up. And then we have MSE, right, for this system. This is MSE test. So if you think about the global performance of the system, it's going to be a balance between trying to find maximized MSE train while not losing MSE test. Remember we had those two graphs. We had the one graph that had MSE train and MSE test on it. We noticed the divergence.
Right.
The divergence is actually going to be the product of these two lines working together, right? So as this one starts to fall off much more quickly down here, this one's getting more accuracy within the training performance, but what happens up here? That one's actually going to start losing relative accuracy. Personally, I honestly think you could get away with moving over there, but notice what happens to it. It's going back up, right? It's going, at that point in time, to get over here to the split point, where's the relative degree from what it is up there? It's going up again by a little ways. What is the thing we want to maximize with respect to a model in general? We want to maximize its utility for future applications.
Right.
So its utility for future applications is prefaced based upon its idea of learning the future tendency. So the reserve set, the testing set, simulates the concept of what would likely happen on the new data. So if we saw any decrease in performance on new unexplored data, we're going to assume that the reason why the model made an incorrect assessment about that data was because it memorized something from the training set. So we're going to err on the side of caution here with respect to the increase in degree of lambda. We're going to say, I'm going to actually let it have a little bit more flexibility so that it will try to find all of the features that are relevant to things even outside of the training set, right? That's actually the goal of this, is to do enough penalty without so much that we lose the generalizability of the model. You want the model to maximally generalize, so you don't want it to become too much of a specialist, right? The ultimate specialist model would be the model that does 100% perfect on only the set of data it's seen. That's an overfit model. The model that literally treats every data point the same, right, seems like a good model, right? What happens there? We say this is the relationship, honestly, the truest relationship of the ethnic and sociocultural implication of the term bias. A certain amount of bias is necessary in order to be able to have actual fair treatment of system value. You must make certain predeterminations on the origin characteristics of the individual that you're dealing with in order to sort of treat them where they live. That understanding of bias becomes a situation where I say it's just past experience. It's just what I have learned, right? It's not applying it in a malicious way. That's how the term actually gets used, is that bias gets applied maliciously, but attempting to understand where someone lives and where they come from, and then working to try to generate a model that explains to that person where they live, guess what? That actually is an improvement. So I make assessments in this class, right, about what classes you've taken in the past and what information you understand. I also make assumptions about what I've taught in the past and how that implies to be able to create value for you to learn in the future. But not everybody gets it. My goal, however, is to try to maximize it so that everybody gets as much out of it as they can. I could test those of you who are regular attenders of the class. You'd probably do much better in overall performance than my students that only show up whenever there's 60 people in here, right? But my actual goal is to try to optimize such that everybody has roughly the same level of performance. But if I give a super baby's first statistics test in here, right, and everybody does really well on it, I've still underfit. I've underfit, right? That's the same characteristic. So both are equally bad. Both are equally bad. Like I said, this is the definition. The most basic definition of this is compromise, right? The definition of compromise being the best type of compromise being where everybody leaves slightly dissatisfied, okay? The model says, look, I'm not going to be able to maximize you training data. I'm not going to be able to get the best out of you because guess what? You just don't perform up to the standard whenever I increase the flexibility of the model, right? So say, hey, I got to stop early for training because testing is starting to lose accuracy, right? Effectively, I could keep improving performance in training by increasing the flexibility, but what am I doing? I'm attempting to maximize variance capture, which is standardized by the R square on the training. Maximization of variance capture. Notice here also what happens. The actual R squared, the improvement of R squared MSE over here, is actually quite a ways from the crossover point. That one's weird to me. That one's weird to me. Let's look also at L2. Let's look at this just quickly, because I want to get through it or get over to it to where we can look at it. We already know everything that's happening in this graph because it's effectively the same thing. But what happens when we square it? Everything just happens much faster, okay? It's like, it's totally flat, totally flat, totally flat in terms of training performance, right? And then all of a sudden training performance goes MSE, right? So it starts off with low MSE, almost no error whatsoever. And then all of a sudden it goes straight through the ceiling. It just makes a hole right through the ceiling, like a rocket, okay? This is more what we're used to seeing, honestly, because MSE means squared error, and the L2 regularization both deal with squares. As a result of MSE and the square of the coefficient value being in the same scale characteristics, we see the change in scale characteristic more indicative of the offset here. But still notice, we have to stop lambda at some point in time before the max crossover value, right? Max crossover value would be somewhere in here. We're actually going to stop it back here. Now, the other thing that I think is interesting is what would be the advantage of stopping it out here? It would technically be more consistent between train and test. This is something I wasn't really planning on talking about necessarily, but let's look at it. Let's look at it close up. I'm going to go all the way. I'm going to plot into this system. All right, we're going to get insight. What's happening to the training error? It's going up. That's actually the exact opposite of what we want.
Right.
Why? We say, well, testing error is the only thing we're concerned with. Not exactly. Not exactly, okay? Early on in the class, I would say, yes, we're only concerned with testing error. That's just to simplify the problem. That's just to make sure you understand what the goal is. But let's think about this. If 70% of the data is tied up in the training, and only 30% of it is used in the testing.
It's weighted.
Doesn't that mean that whenever we're making this assessment, if I choose my lambda based entirely off of testing performance, I'm doing what? I'm disadvantaging the model. I'm saying, I'm making an argument that only the new data matters, only the performance of the new data matters. No, it is not only the new data that matters. It is effectively the value of a balance between maximization of training accuracy while maintaining a relative lack of reduced performance on the testing. Now I say reduced performance on the testing comes when it does two things, either underfits or overfits. The underfit should be what? Consistent between training and testing. An underfit in training and testing should look exactly the same because it does what? Describes neither well. Both are equally badly described by an underfit model. That's the interesting part of it. Overfitting benefits the training while taking detriment to the testing. But underfitting just underfits both equally well. So notice variance maintains a relatively static initial descent that then starts to drop off. Then what happens here when it's underfit? Right? The variance is low. Both are performing equally badly. That's what the variance means there. Right? Yeah.
So is there like a data set with a sample size where you would break the 70-30 and kind of go closer to maybe 50-50? As you're like maybe using cross-validation methods?
As n increases radically, you could utilize a very high test train split offset. We actually tend to push down maybe towards 60% for training in some neural networks models. All right, I've seen 60% used so there's three players here, right? You've got relative model flexibility with respect to features, and you've got sample number. So you have sample number and features. What do you have as a loss for training offset? More features, higher dimensionality. If you include less samples for that relative dimensional space, you're running into the curse of dimensionality. So on the bottom end of low end for training set, curse of dimensionality. On the top end of sort of overtaking, you don't allow sufficient samples to be able to adjust for overfit, right? Or to be able to adjust for variance between sets. The idea of a 50-50 would be what? It'd be treating the training and the testing equal with respect to their the predictive capacity characteristic. We know there is a diminishing return on reducing the number of samples as a result of relatively high dimensionality systems. So if the dimensionality is kept relatively low and the sample number is relatively high, and the rough individual variance of each of the samples, the sigma square it brings in to the overall consideration, you can leave the dimensionality relatively high, increase the split amount, and be a little bit more confident about symmetrical performance between the model, effectively saying that you can be more confident that it will perform well in the future. But in truth, you're going to have to determine this experimentally on your own. It is not, there is no theoretical baseline for that number for me to be able to give you a ratio or an offset, because I can give you sort of a composite score that, in which you could attempt to take all those factors into consideration. But think about it this way. Imagine each one of those things as being a score penalty that I tack onto the end of the RSS. Where I say, you can rescale the data set to this degree as a what we call hyperparameter, right? A hyperparameter is how much effective splitting, how much we're reducing the training model to try to give us more testing. What happens with k-fold, right? What happens with k-fold? The lower the k-fold, the less of the training data is going to be used to the more of the internal testing. The higher the k-fold, the more of the training data to less of the internal testing is going to be used. If we do higher k-folds across more systems, we try to understand what the likely variance would be of a future external data set that would have a small subset of the same characteristics in it. But what happens then? Smaller data sets are more prone to weird variance characteristics, right? Because when you try to take the average or you try to take the standard deviation of a small data set, one or two samples that got picked out randomly in the system that are maybe more in the outlier range would do what? They could pull the mean of that system way over, right? So it allows for this, anytime that we have a smaller testing set, we create the possibility of creating a very, very bad scenario for the training's comparison. Too little training data, too little training data creates a model that doesn't get a big enough picture, doesn't see the whole entropy of the system. So it can't learn from all possible examples. Too much training data means too little testing data, which means that the testing data can have weird variations that make it not an actual good example of potential future outcomes. So it is always going to be a trade-off based upon the relative variance of the data that you have, the variance within the training and the testing set, as well as the dimensionality of the model and how much variance capture is happening within the prescription of that initial training set. So playing around with these factors where we use cross-validation to characterize something like lambda, as well as to characterize something like the fold sizing, and to characterize potentially selection of individual features, is the mechanism by which we try to utilize the data itself to drive the system. Next, we're actually going to talk about another mechanism by which we can use the data itself to try to drive for a minimization, and that is the bootstrap process. And that's the selection with replacement of individual data sets. We keep the data set scaling the same, but we effectively duplicate individual samples with the assumption that, given the same density, that if we oversample a region, we would end up with a potential alternative version of the original sampled space. So we can build multiple simulated versions of the data set to see what it would be like if we continue to resample the original core data. We'll talk about, I went way over today, sorry guys. Thank you very much for being patient with me, and I'll see you guys on Wednesday, but we'll talk about Bootstrap. Stay warm.
I just feel like I have too many knobs and a no-win scenario, and I'm trying to